Hello, welcome back. Uh, this is the last part of our discussion on copula. In the previous video, we discussed several topics under copula. We discussed what a Gaussian copula is and some topics, theory regarding how to construct a joint CDF using a copula, how to generate data, again, some theory. And then we looked at some examples, theoretical examples. In this video, we are going to look at some specific examples and also a brief discussion about R packages and functions available for copula modeling. So in the last video, I gave you the theory required to generate data using a Gaussian copula. Right. One important thing is that we need to get an expression for this joint, sorry, the conditional distribution, conditional CDF of V given U. And I showed you the expression that we derived uh, after several steps. We showed that this is the expression required to get the conditional distribution of Y given U. This is required when you are generating data using the Gaussian copula. So the procedure was first to generate two standard uniform random numbers U and W, and then let W equal to that conditional cumulative distribution function. So W is equal to this expression, therefore, and then from that we can get an expression for V. Right? So this V and the previous U are correlated. There is some dependency between those two. And after obtaining U and V like this, we can transform them to the required X star and Y star, where X star has the required uh, marginal CDF and Y star also has the required marginal CDF. Right. So like this, we transform U and V generated in the previous steps to X star and Y star. And then we can show that the CDF of X star is the same as the required CDF of X, and similarly, CD of Y star is the same as the required CD of Y. And we also stress the fact that the joint cumulative distribution function of X star and Y star is not necessarily equal to the actual joint CDF of X and Y. The joint CDF for X star and Y star is equal to this expression here. But this is a joint CDF, but not necessarily equal to the actual joint CDF of X and Y. This is the CDF generated by the Gaussian uh, copula. But if we calibrate the parameter rho so that the Pearson correlation between X star and Y star will be equal to the required value R, then the required covariance structure or the dependency structure will be preserved, uh, at least approximately. Right. So that's what we discussed at the end of the previous video. So now we will look at a particular example where we, in particular, want to generate uh, observations uh, xy, where x we need to have, for x we need to have a standard normal distribution, and say for y we want a standard uniform distribution. So those are the required marginal distributions. And let's use the Gaussian copula for this purpose. In this case, I'm not going to calibrate the row in the Gaussian copula. I will generate the data without calibrating, and then we will finally check what the actual correlations in the generated data x star and y star, right, between x star and y star. Right. So create a bivariate distribution on negative infinity to positive infinity time 0 to 1 as a normal copula with standard normal and uniform marginal distribution. So here the question is telling us to consider three possible values for rho, three cases, rho equal to -7, rho equal to 0, and rho equal to 0.7. As I mentioned, I'm not going to calibrate in this case. I'm going to see what happens when we generate without calibrating. Right. So for each required value of rho, generate an observation xy as follows. Actually, we are going to get x star, y star values, not really xy values. So first thing, as explained earlier, generate two independent standard normal uniform standard uniform observations. Generate two independent standard uniform observations. That means U and W are coming from uniform 0, 1 distribution. And then create or generate or calculate or obtain a V using this equation. Here we use this U and W to create V, where this V also is, according to this generation, V will be uniform, and there will be a correlation between U and V. That correlation between U and V will not be the same as rho. It will be something different, but still U and V will be correlated. So thus U and V are dependent standard uniform observations having Gaussian copula 0. Now, if we, for example, calculate Z1 to be pi inverse U and Z2 to be pi inverse V, then the correlation between Z1 and Z2 will be equal to rho. But the correlation between U and V will not be equal to rho. Now, what we are going to get is not even U and V. We want to now transform U and V into X star and Y star, where X star to have a normal distribution, standard normal. Therefore, I have to transform this U using inverse cumulative CDF of a standard normal. So therefore, X star is equal to capital pi inverse U. And I want V to have a uniform 0, 1 distribution, and V, according to this generation, actually already have a uniform 0, 1. Therefore, I don't have to separately take again the inverse of the CDF of uniform 0, 1. Right? So I can just take Y star as V in this case, because we know V already have a standard uniform distribution. So these two are the required observations, and then we'll have to do it again and again and again to get more observations. So I have written down here some codes, R codes. So I'm going to generate 2500 values. Row values are -7, 0, and +7. As I mentioned, I'm not going to calibrate them. So first take, okay, I'm going to take all the 25,000, 2,500 values at the same time instead of doing it again and again and again 2,500 times because in R we can work in vectorized fashion, right? So U will be containing standard uniform random numbers 2,500 and W will also contain standard uniform random numbers 2500. And then in order to get the normal uniform data, right, X and Y has to be normal and uniform, we use this because I have to get this, do this for different values of row. The function is written to get those things separately for row points negative zero point 0.7, 0 and zero point 0.7. This is that part. So what we do is we get for a given row value, right? When row is equal to row values ith value, v is given by v is calculated using this formula here. So that is this expression p norm. Right? P norm is this pi, and then row times this is q norm u plus square root 1 minus rho square. This is again q norm w. Right? So that's what I have written here. V is going to be obtained using that expression, right? For a given I, and then x will be q norm u, right? That is to get standard normal, convert u to standard normal, but y will be the same as v. So that will be done for each row. And thereafter that, I can separately get them. And what I have done is I have actually drawn um, uh, the scatter plot of y versus x. And also I have drawn the histogram. I have drawn the histogram of x and y. And also, yeah, for all three cases, I have drawn those. So this is the command to get those graphs here. I'm not going to spend too much time explaining those. Right? For each I plot the data x values and y values. That's giving the scatter plot. And also I do the histograms for each x and y. Right. So then I get this graph. These are the scatter plots. This is I obtain you this graph, the data using rho equal to -7. But when I get to those x star and y star values, I calculated the Pearson correlation coefficient. You can see that's -0.68, 0.68, but pretty much very close to that row value. So it looks like in this case, actually calibration is not really necessary. All right. Because the correlation between Z1 and Z2 is approximately the same as the correlation between X star and Y star. And when rho is equal to 0, this is the scatter plot of Y versus Y star versus X star. And the sample, in this case, there are 2,500 values, N equal to 2,500, R is equal to 0.02, so which is very close to 0 again. When rho is equal to 0.7, this is the graph of y versus x. In that case, r is equal to 0.71. So see that rho and this r are pretty close, right? So it seems that any calibration is not really necessary here because uh, from this joint distribution, actually, we can see now what marginals we can get, right? And we will see actually, if you, for example, these are the marginals of X star values. You can see that those all are very close to standard normal. We see 0 here, almost between -4 and 4. And like this, all these are uh, pretty much standard normal looking. Right? These are the three cases. So you can see that marginals are what we really want. And then these are the marginals for the Y star values, right? So we expected them to be uniform. Actually, you don't get a flat histogram when flat graph when you get a histogram. So this looks pretty much okay as considering uniform distributions. Right. So that was how to use the Gaussian copula to generate bivariate data having standard, normal, marginal for one variable and the other one standard, uniform, marginal. Now let us look at another example where we are going to generate some data, XY values, where marginal of X will be beta 2 phi distribution. Marginal distribution of Y will be beta phi 2 distribution. So both are beta, but parameters are different. And now I say I want the correlation between X and Y and thereby correlation between X star and Y star value to be zero point 0.6. Right. So in this case, I'm going to consider calibration so that the data will have zero point 0.6, not correlation, not the correlation between Z1 and Z2. Right. So rho in the copula is actually standing for the correlation between Z1 and Z2. Right. So we are going to choose a Gaussian copula. So we are going to assume that corresponding U and V values will be the Gaussian copula. Right. So X is going to be calculated using the inverse cumulative distribution of the beta 2 phi distribution evaluated at U. Y will be calculated again using the inverse joint cumulative distribution function of a beta phi 2, sorry, not the joint cumulative. X will be the inverse cumulative distribution function of a beta 2 phi distribution. Y will be the inverse cumulative distribution function of a beta phi 2 distribution evaluated at V. Right. And what we want is this correlation between X and Y, in other words, correlation between these two to be 0.6. Right. So therefore, we are not going to say rho is equal to zero point 0.6. We are going to find out a suitable value for rho first by using a method and calibration method, and then put that value as the rho in the Gaussian copula. Right. So this is what we do for the calibration, right? So for the calibration, it's better if you consider as large number of observations as possible. So here I'm considering 50,000, but if you can have more than that, that will be much better. So what I do is I generate standard uniform random numbers 50,000, and that's called U calibration numbers, and also get another set of 50,000 random numbers from standard uniform. They are called W calibration. And then these U calibration numbers are going to be converted into beta 2 5 random numbers by so they are called X calibration. So those are the X values that can be done by calculating the inverse cumulative distribution function. In other words, quantile function, Q beta function evaluated at these U values. Right. And then, so I'm going to keep that as X. And then in order to get Y values, I'm going to again consider two calibrations using, for example, I'm going to convert these U's into standard normal using Q norm. So this is taken as A calibration. Right? So those are standard normal. And then again, W is going to be converted into standard normal. So this is called B calibration. So what I want is actually, so these are actually Z values. A calibration and B calibration are Z values. I want the uh, So V calibration. So X calibration is obtained here. V calibration, as used in the previous formula, calibrated V values are obtained using P norm, rho times A calibration, and so on. So this is a function of rho actually. I'm considering this as a function of rho, where I want to find out the rho. So this is the function that I will be using to find out the calibrated rho. This function is I have named as R beta Pearson. Right? You can call whatever you want. So that's a function, right? So Y calibration will be then Q beta coming from the V calibration with parameters 5 and 2, right? So Q beta. So that So what I want is actually later on to calculate the correlation between X calibration and Y calibration, right? So V calibration will be coming from this function here, right? So when we use V calibration using Q beta, Y calibration will be given. And then finally from this function, the output will be the actual correlation between X calibration and Y calibration. So what I will do is I will solve that equation R beta Pearson rho, so which will give you the correlation between this and that to be equal to zero point 0.6, and then solve that function because that function is going to be a function of rho, and that function R beta Pearson within bracket rho minus zero point 0.6 equal to 0 is the equation that I have to solve to find out the suitable rho value, right? So here I do that, R beta I call it, and then use the function uniroot to solve because it's a function of rho only. I use the function uniroot. So the function that I consider is a function of rho, that is R beta Pearson rho minus whatever the R target value. R target value is 0.6 here, right? And then I have to give an interval to look for that rho. So I give interval as this one. So that is how you use this uniroot function. And then once you use it, and then in the output, there will be a component called root. I extract that by putting $root. So that will be rho beta value, right? I call it rho beta. That is what the calibrated value that I should be using in the Gaussian copula. So when I calculated, when I solve this equation, for rho, then I get rho to be equal to 0.633. Right? So you can see that there's no much difference actually. What I want is uh, the correlation between Pearson correlation between my generated data to be zero point 0.6. For that, rho in the uh, uh, Gaussian copula should be 0.633, right? So again, you can see there's no much difference, but we will be using this number anyway, and then checking whether we have approximately zero point 0.6 again between X star and Y star values. So use the calibrated value in the Gaussian copula generator defined earlier, right? So I have already defined the Gaussian copula. So use that uh, with this calibrated R, uh, and then, right, so here is the Gaussian copula function, right? So there I have to give the number of observations, and I have to give the calibrated rho value. Calibrated rho value is actually 0.633. And then I have to give, this is general function that I have written. Once I get U and V, then I have to apply inverse CDF of some functions depending on what margin I want. So in this case, this RQX is a function to get the margin of X, margin distribution of X. This RQY is also a function that I have to input to get the margin distribution of Y. So in this case, actually, RQX will be just will be applying into the vector U coming from here, and then RQY will be applying to V that is coming from this one, right? And then finally, I can get the whole data frame, including UV, XY, and also if you need um, Z1 and Z2 can also be obtained. So this is the formula that I will apply, but n will be whatever 10,000 and C rho will be equal to 0.633, and then RQX will be actually Q beta function, Q beta 25, and RQY will be Q beta 52. So here I have applied that thing. So here my data, I will call it beta data. So I'm applying this R Gaussian copula function. This function with n equal to whatever 1,000, here I'm going to generate 20,000 values. C rho will be the rho beta value that I have already obtained, that is 0.633. And this is where I input the function QRQX. RQX is the function that I use to convert U into X star value. And that is in this case actually Q beta U 25. The other function is Q beta that will be applied for V phi 2. So these are the two functions. So when I apply those things, Q beta will be, the data will be stored in that name, beta data. And then if I want, I can separately calculate mean of X values, generated X values, variance of those, mean of Y variance I have calculated, and also the Pearson correlation coefficient between generated X and Y values. I call it beta summary here. So those will be here, right? So the quantile transformations give the required beta marginal distributions. We can see that here, right? Right. So this is the required value because that I am expecting beta 25. So the expected beta is equal to alpha divided by alpha plus beta. So alpha is 2, beta is 5. Therefore, I expected value of the generated X values to be 2/7. This is the value that I have got out of those 1,000 values. So you can see that these are pretty close. And similarly, the variance of a beta distribution from using that formula, this is the expected variance of X, and this is the variance that I got uh, from the generated data, X values. And similarly, expected Y value is 5 divided by 7, that is 0.71, and this is what I got. So again, you can see pretty close. So you can see that the generated XY values actually have the expected mean and the variance of a beta distribution. And also when we draw the histogram, again, we can see that it has a shape of a beta distribution, right? So that's a kind of a confirmation that the data actually generated have the required marginals. But this is the joint distribution, right? The scatter plot of the data X, Y versus X, the generated data. By the way, we wanted the correlation, Pearson correlation coefficient between the generated data to be 0.6. So therefore, we actually calibrated rho to be 0.633. So once we input that calibrated rho in the copula, the generated data have 0.6084. So it's pretty close to the expected or required correlation also. So therefore, this is that using the Gaussian copula actually, in this case, we can get the data as required, right? That means the marginals to be required, marginals to have required beta distributions, and the correlation between X and Y to be as close as possible to 0.6, right? Okay, so what can we say about this result? The beta marginal distributions are exact properties of the constructed model, right? Discrepancies in the histogram are just ordinary sampling variation. If you have large, if you generate more observations, actually you will see the pictures more matching to the curves, beta curves that I have drawn. The target Pearson correlation is attained approximately because rho is calibrated numerically and the final sample is finite. The constructed joint CDF is actually this one. This is the constructed joint CDF, but we are not interested in the actual joint CDF here. If we want, we can get an expression for the constructed joint CDF. So that is given by this expression. The margins and R equal to 0.6 do not uniquely determine uh, this joint CDF. The Gaussian copula is an additional modeling choice. Right. Right. So if I look at the summary of the examples that we look at, we can say the following. The copula associated with continuous xy is the joint CDF of u and v, where u is defined as fxs and v defined as fyy. Then the unique copula is equal to the cumulative distribution function of this u and joint cumulative distribution function of this u and this v that we saw at the beginning of the lecture. If the joint distribution is known, of course, then we don't need this copula method to generate data. In that case, actually, we can use the previous method that we have already discussed in a previous lecture. That is, from the known joint cumulative distribution function, we can get the conditional distribution density function of y given x, right? So, and if you know the marginal of x, you can get data from that distribution. And once you have got the data x value, then you can generate y value given x using the conditional distribution of y given x. So, if you know the joint density function, you can easily do that. So, in that case, actually, we don't need a copula method to generate data. That method was discussed in a previous lecture. Where we need the copula method is actually we want to generate data so that the marginals will be the given marginals, and the correlation or the dependent structure will be as whatever the given structure. And the joint distribution, actual joint distribution, that means the cumulative or the density function is unknown. In that kind of situation is what we need the copula method, right? So in that case, what we do is we select a suitable copula, a known copula, and then apply that copula with the given marginal distributions to generate the data. In that case, of course, we have to calibrate whatever the parameters in the selected copula. Okay, so to end this video, I have included a brief description of R packages and functions available for copula modeling. Because in general, when we generate data using R, we don't actually write down the previous functions like what I did necessarily, because R already has some built-in functions available, making the generation of data much easier, right? For example, we don't have to derive expressions like this, right? Otherwise, we'll have to get V in terms of U and W. So getting this kind of expressions is not that easy. So if we use the R functions available through the package called Copula, right? Then we can generate data much easier. ways than what I have shown. What I have shown, this is actually how you really follow the theory to generate data. That is just to understand the theory behind it, right? But when you practically actually generate data, there are so many built-in functions available in R. So here is a brief description of those functions. I'm not going to show how to apply these things here because there are help always that you can get to see how these functions are applied. But most of those functions are available under library Copula. So therefore, you have to install the package Copula first and then call it using the library copula. So these are the available copulas, right? Normal copula, that is the same as Gaussian copula, and another one called T copula, Clayton copula, Frank copula, Gumbel copula. So those are different copulas suitable for different situations, right? The capturing different types of dependencies between the required variables x and y, right? And then in addition to those, there are other functions like starting with P, D, and R, like for some other distributions, like P norm, Q norm, R norm, and so on. We have functions called P copula, D copula, R copula, and so on. So P copula will be evaluating the copulation CDF function, right, for a given copula. D copula evaluates the density coming from that, that is coming from the derivative of the P copula, and R copula will be generating the data from that copula, and then probes for transforming observations into pseudo observations, and fit copula for estimating the parameters of the copula uh, from data, and so on. Functions are available, and you can always get help to see how these functions are used. In addition to that, there is a function called MVDC for constructing the multivariate distribution by combining a copula with specified marginal distributions, and then some other functions like this. Right. In addition to that, there are other packages like wine copula and R wine copula. They are packages containing more functions to generate data using copulas. Right. I have just applied those built-in R functions to generate data from those two beta distributions, as I have already looked at. And these are the codes required for that. Again, I'm not going to explain each of these things. But anyway, I require the to install Copula and then call it library Copula. And then I have to anyway calibrate. So calibration part is still required because I have to give that value as row, right? So calibration is done, very similar to what I did. And then after that, actually, I have used the built-in functions to generate data, right? So that is the end of this video, and that is actually the end of all the parts of chapter 3 also. Right? So in this chapter, we looked at lots of uh, topics. So let me show you what the topics that we looked at. Mm, yeah, something is wrong here. This shows only the copula topics, but we have looked at a large number of topics. So let me see whether I can get it in a minute. I'm running all the contents of chapter 3 together. Then only it shows me all the contents. In the previous one, I had only the contents of the copula. Right now, I'm running all the contents of chapter 3. Then it will show me all the contents that we discuss in chapter 3. But it will take a few seconds because there are so many, about 500 pages altogether, 500 slides. Right. So these are the topics that we have looked at. These all are in different videos, right? So we started with a joint uh, and marginal CDF, joint and marginal PMF, joint and marginal PDF, so on. So joint distributions. And then expected values, definition of independence using the conditional distributions, and also joint distributions. Also here we define the independence using the joint distributions, and we looked at some examples, and then we discuss about the conditional distribution in I had very lengthy discussions about that. Conditional mass function, conditional density function, generating data. This is where I mentioned that if I know the uh, actual joint distribution, we don't have to use the copula method there, right? What we can do is we can get the conditional distribution of, say, y given x, and if we know the marginal of x, then generate one observation from that marginal, and then given that x, generate uh, a value y using the conditional distribution of y given x, and then those two will jointly have the required joint distribution. So in that case, we don't need copula method. And then we define the independence in terms of using the conditional distribution. Then we looked at some Bayes results, conditional mean, and so on. And then we discuss about mixture distributions and Bayesian statistics, Bayesian classification. We looked at some interesting examples. And then we discuss about the random sum, distribution of random numbers of random variables. Right? And then we derived actually expected value and variance for that kind of random variables. And then we also discuss about covariance and correlation, linear regression. This is linear regression for the population. When you have joint distribution between x and y, we can talk about least square regression line uh, for y on x. And then we discuss about the distributions of order statistics. I use some apps, right, to generate the distributions of the minimum, maximum, and so on, right? Shiny apps. And then we discuss about today, we discussed the distributions of transformations. There we discuss about the univariate transformations and bivariate transformations. And then finally, we we had a lengthy discussion about copulas, right? In the book, actually, in chapter 3, there's a very little amount about the copulas, but I thought I will have a kind of a comprehensive look at it because it's a very important area nowadays. So anybody watching this video and the previous video will understand some theory behind copulas, generating data using copulas and so on. So that is the end of this video, and also that is the end of the discussion on chapter 3 of the Dominion course book. So in the next video, we will start chapter 4.